Hello and welcome back to ST118 Statistics and Applications, Session 5. In this video, we will discuss the Wilcoxon signed rank test for one population median test. Wilcoxon signed rank test is a non-parametric test, and there are some characteristics, advantages, merits, and all these that come with non-parametric tests. We have already spent an entire video discussing that because they are common across all the non-parametric tests. So we'll go straight into discussing Wilcoxon signed rank test. So it's one population median hypothesis test, and also known as the Wilcoxon signed rank test. Right. Now, just to kind of bring the outcome up front, this is used in one population median test. And remember, one population, we are trying to qualify, let's say, a particular measurement, right? So we consider a whole population of repeated measurements on the same item or multiple repetitions of the same item in real life. And we are going to use Wilcoxon signed rank test to test on the median rather than the mean. Okay, so we are still trying to test for the center of gravity, right? The one point, one descriptive that summarizes all the population measurements. So we will use the median as the point of test. So again, it's the same thing. We need to sample, and then we need to take the sample median as a point estimate of population median, but also we need to consider the variations, right? So the deviations from the median and all that, and that's why we have the hypothesis test, right? So we'll illustrate using an example. To show the mechanics of calculation. So these days it's very easy to calculate the test statistic for Wilcoxon signed rank test, and for that matter, almost all other non-parametric tests. Not so in the earlier days, and as a result, you can understand why this inefficiency, right, this lack of access to quick computation of the test statistics, p-values, lead to a reluctance to put them in the class syllabus, right? So it has a chain effect. So most of you should see a statistics syllabus that doesn't really talk much about non-parametric tests. And while it has got a lot of benefits and usefulness to both, right, the computing person, the statistics, the outcome producer, and the audience, the consumer of the statistics, calculation wise, it can get very intense, right? Especially in the calculation of p-values, and the test statistics themselves are also they are not complex, but they are just tedious, right? So you need like few processing steps before you get to the test statistic, and then understanding what does that mean, what does the test statistic mean, is also, I mean, it's similar to the parametric tests, but not so direct, as you will see. Okay, so we'll use an example to discuss that. Now, not forgetting that we are doing one population median test, right? So the real life situations or reasons why you want to do this, they are very similar to the parametric tests, i.e., we are trying to, right, assess judge or make decisions based on certain fixed standard, right? Do you meet the standard or not? Do you qualify for Olympics marathon run or not, right? You need to be at certain running level or not, right? So we are trying to have a standard level, and we want to judge or decide or qualify, right, or assess certain measurements, right? So that will be the motivation to use one population test. Then as for why median, the moment you use non-parametric test, then you need to use median. And if you use parametric test, then parametric test couldn't quite compute median, so they use mean. All right. So as you see, the choice of test already somehow already has picked the choice of center of gravity. And if mean and median in the population doesn't align, which means it is skewed, right? Yeah, because if they align, then mean equals to median, then very likely the whole population is very symmetrical, low-key. But if they are having a gap, especially a big gap, then you likely have a population that's lopsided to one side. We call it skew, right? And that's why for skewed distributions, your choice of parametric and non-parametric test already, in some sense decide on the quality of your outcome. That means, is your conclusion reliable or not, right? So that's the reason why. Okay, so let's look at an example straight. So our hypothesis will be H naught eta is equal to, normally we'll put 0, but I will just illustrate with a non-zero example such as 5. And this is again the hypothesized median, much like we have a hypothesized mean, right? So hypothesized median. Okay, so let's suppose we are wondering whether the population median is 5 units or not. So that's our hypothesis statement. Then we begin sampling, just like parametric test, because like I said earlier on, sampling is the only way that statistics touches reality. So one measurement, one touch, then you feel the shape, right, of the population data cloud. Okay, so because it is a manually written process, I will just use a small sample size, right? So let's say X is the sample. We have 3, 2, 5, 10, 7. Okay, so that's all. Okay, so very, very simple. Clearly, n equals to 5. Okay, now what? So we want to test the hypothesis, and we wrote down that hypothesis. Next thing is we want to calculate the ranking. All right, so the ranking. Now, but we need to the median, hypothesized median is 5 and the sample size is 5. But this is n, this is eta, this is Greek letter. Remember, Greek letter represents population parameter. So the left leg is a bit shorter. So we need to account for the fact that it's non-zero, or because the steps involved in Wilcoxon signed rank test, right, and many other non-parametric tests, they are centered at 0 on the right side. But it doesn't mean we cannot use a non-zero hypothesized median. It just means that we want to zero off. Okay, so we will instead calculate why do I call it X here? Okay, so let's say X. Okay. So the adjusted X will be 3, 2, 5, 10, and 7. Right, so we have -2, -3, 0, and 0 is something interesting, right? So we want to talk about that. because there's a special treatment for 0. So 0 is to be ignored. Zeros to be discarded in our computation for the test statistic. Okay, so we want to throw that away, more because it is causing problem. So we are going to look at the positive ranks and the negative ranks. These are not ranks, these are values, right? We're going to rank them because they are also repetitions. So right now, our so-called net data will be this set over here. Now, if the median is, the hypothesized median is not 5 but 0, then we'll go directly here, right? So we don't have to minus anything. So in this case, our data will just be -2, -3, 5, and 2. All right, so we can start to rank them. So let's say we put them over. Okay, we put them over. We'll rank them. Okay, we have the absolute values, right? So the absolute values are 2 and 2. So these are, so if we ignore 0, then 2 and 2 will be a tie. Yeah, in this case, rank starts from 1, not 0. Right, so it is like first, second, but you cannot say -2 and 2 because we are considering the magnitude only. Huh? So -2 and 2, they are like the same. So we will have a tie, and so we will call it 1.5. So it's rank 1.5, 1.5. Ignoring the signs. Well, so at first ignoring the signs. So it's like absolute rank. So next up is third place, number 3. So number 3 is rank 3. And notice that we jumped away from 2, right? Because 1 and 2, they share. So 1 plus 2 divided by 2. Okay. If you have 3 numbers, then you have to add the extreme. So 1 plus 3 divided by 3, right? So that's going to be, no, sorry, 1 plus 3, you want to get the middle one. So 1 plus 3, 4 divided by 2, so you get 2. So here we get 1.5, and this one is the 4th rank. So 5 here gets a rank of 4, like this. So that's absolute rank. Okay. Then what we want to do is to add up the ranks based on the signs, right? So in some sense, we say the positive ranks. Okay, which we normally denote as W plus Wilcoxon, no doubt, is the sum of all the positive ranks. So we scan through and look at the positive ranks based on the original data, that is, right? So 4 plus 1.5, so we get 5.5. The negative ranks, similarly, all right, and we scan through the ranks, noting for the minus signs. So we have 1.5 plus 3. So that's 4.5. Okay, that's it. We have got our 2 ingredients to the Wilcoxon test statistic, which is W. So W is going to be the minimum of W minus and W plus. So we get 4.5. So that is our test statistic. So this is it. right? So you can see why I cannot just give you the formula. W equals to minimum of W minus W plus, because it will invite the question, what is my W minus, what is W plus? Right? So you have to go through this, and the thought process is not difficult, right? But it's just tedious. You need to be very careful and ignoring zero, untying the shared ranks to make sure it's so-called fair, right? It's neither both rank first nor both rank second, right? And it's ranked kind of like an average out basis, unbiased, right? So neither leaning to the larger number or smaller number. So this is our test statistic, and as you recall in parametric tests, we need to then compare it with the distribution associated with the test statistic, isn't it? Yeah. And if you search around, you'll find tables. So we're back to the Z table, T table days. Why? Because calculating the distribution is hard, very hard. Right? Okay, so running a Python package, scipystats dot Wilcoxon, I managed to get a p-value. So use modules, use software modules to get p-value. So the p-value here is equal to what I get was 0.8539. Right. So remember p-value. Anytime p-value is smaller than alpha, then we reject the null hypothesis. See, it's so useful, right? We are now entering into somewhat an unknown territory. We haven't learned non-parametric tests, but already we can make sense of this p-value if, right, the person producing the p-value had verified that this is p-value. So if you call this p-value, then we can use it to check against alpha, right? So suppose alpha, example, alpha is 5%, right? Then now we can conclude, since p-value is equal to 0.85 is not less than alpha equals to 0.05, we do not reject H naught and conclude, right? It's the same template. And conclude that since we do not reject H naught, we will look at H naught and read this out in English, not Greek letter, right? And put it in context. If this is about, we wonder whether the median income of XYZ city is 5,000 US dollars annually or not, right? So if that is the hypothesis, right, the claim, then we put it in here, and then we use 5 doesn't mean 5 units, it means 5K US dollars, right? So put it in context in the relevant unit. So conclude that population median is indeed 5, right? So here we stick with 5, but you understand, right? So you need to write it up more into the context at 5% significance level. So that will be the necessary and complete conclusion that I've been urging you to follow, right? It's almost like a form, just fill it up and that's it. So that you always express the right amount of correct conclusions and derivations, and not suddenly step into some words or choice of words that basically go beyond what your facts or data tell you. Especially things like, therefore, the company should expand their operations into XYZ city. Or therefore, a company should not. So all these are inferred actions or conclusions, right? Because to expand operations or not, there are many other considerations. Or do we do that immediately? Or delay for 1 year, wait for a while, observe some events first, or something like that? It's all judgment call and not directly implied by the data here, right? Is there urgency or not? We can't see it in the data. So that's why I still say just use the template to write this down as a summary of the entire hypothesis test first, right? Once you can write down this, then the summary is clear. You can then consider what did the data show? Oh, data shows that yeah, the population median is $5,000 annually. So it should or we should not. Let's discuss, something like that. Okay. So that's one. Next point is that notice that over here we had discarded the 0, right? So even though we started off with sample size 5, the lookup table, right? So the critical value, which is another way to decide whether we should reject or not, isn't it? Yeah. So we need to look up the WC, right? The critical value for Wilcoxon distribution under alpha equals to 5%. The critical value depends on n and alpha. Not surprising because Z and T also, T especially, well, depends on n and alpha. And the thing is that the critical value, right, oftentimes for small sample size, like n equals to 5, is very small, very small. So it may be just 2 or even 1 if you look up the tables. And over here, we have a very interesting set of data where we discarded the 0. So this n is 4 here, right? Not 5. Because to the distribution table, they didn't see the 0. 0 does not affect or change, yeah, the calculation of test statistic. So that's why it is important to discard them and adjust accordingly when you look up the table. Because that's number 1. Number 2, for n equals to 4, critical value is, if you look up the table, some tables are not even showing that. So minimum value is 5 or more. So is approximately 0. Okay. So in other words, almost any test statistic will not be less than. Okay. So our conclusion, it's helpful to see the critical value version. So we say that another version, since W equals to 4.5, let's call this equal to WC, okay, is not less than. So it's always kind of like a left tail test. If you draw the distribution, the test statistic, the Google pin, has to be on the left side, has to be lesser than WC, which is 0. But it is not, right? In our case, it is not. If it is less than 0, but it's impossible, but suppose it is less than 6, right? Then we reject. So in this case, we do not reject. Same. Okay, from here on, it's the same. H0, and conclude that population median is 5 at 5% significance level. I feel a necessity to write out the same just to show that it is the same. All right. Even if you use the test statistic version, it should always follow the p-value version. There will be no case when p-value you do not reject. You turn to test statistic version, it rejects. Then something is wrong. Okay, so maybe your test statistic is wrong, p-value is wrong, or whatnot. Okay, so just check. So they are always in sync. The only thing here is that I want to illustrate is that the tailness, right, for non-parametric tests is a little bit twisted. because over here we have a two-tailed test. We should call this a two-tailed test. But looking from the distribution perspective, we choose the minimum and see if this minimum is very, very small, right? Even smaller than the critical value, so as to make it very rare, and then we will reject H naught. Okay. All right. So that is for the two-tailed test. If it is one tail, then we look at the one of it, W minus or W plus. Now, so if it is one tail, suppose it is eta less than 5, eta greater equal to 5, then we, if it is less than, right? So so then we look at W1 to see if the negative side is even very, very extremely small, smaller than the critical value. If it is on the alternative where we say eta is greater than 5, then we want to see, does the test statistic, right, the plus side, go, is it the plus side, is it still very extreme? Right? So then we can check accordingly. All right. That pretty much is our example, because we want to reach the statistical conclusion here, yeah? And that's it. Okay. However, out of curiosity, I was wondering, right? I hope you are wondering as well. How does the distribution of Wilcoxon test statistic look like? And this part, if you search around the internet, or if you ask ChatGPT, it's not so easily available. So I tried it out, and let me try to share the results of what I found. Here, it's always positive, right? So it's always positive. And for a sample size of 3, so this is the W test statistic. In other words, we can actually use this graph to find the p-value. So for 0, and we can have 1 here, 2 here, and 3 here. So need to, of course, qualify a little bit. What am I drawing? So this is under the hypothesis that H naught is eta is 0, H1 eta is not 0, and for this the sample size is n equals to 3. Okay, and what did I see? I saw basically something like that. Like a uniform distribution. Okay, now clearly most of the time we will present it as bars, but actually they are sticks, right? So in other words, they are only defined on the integer values themselves. So the critical value is always an integer. Like I said, for example, for n equals to 4, it is 0 or more, as we can see now, right? The moment you step into 1, you're already covering how much? Maybe 25%, because this is 25%. I should be showing this as a fattened bar, right? So the 0 has a meat, has an area, has a meat of 25%, 25, 25, 25, right? So moment you step into 1 is already saying that your alpha is, or your p-value is 25%, very, very large, right? Not acceptable. Therefore, when n is 3, haven't drawn for n equals to 4, but for n equals to 3, anything, right? Any test statistic you calculate that is, likely going to be more than 0, right? A positive number. So end up you will get the failure to reject H naught. Or that means, in other words, the sample size is too small. You are unlikely to be able to reject H naught when you just touch reality a few times. All right. So here's a good lesson, right? So earlier on, we learned that in the previous video when we talked about the advantages, benefits of non-parametric tests, right? That one of it is that, hey, it is very comfortable with small sample size. you don't need to work very hard, right, to make sure the test works. And that is not wrong. The test can work well in its own DNA. That means by construction, by the whole procedure, it is it can be scrutinized and the conclusion is correct. So, however, it doesn't mask the fact that touching reality, the reality part, all right, not the internal engine part of Wilcoxon test. The reality, understanding the reality part. If you touch one time, you only know a portion, very partial view of the reality. You need to necessarily touch, right? Just like the four blind man and the elephant, right? You need to just keep touching, having a large sample size in order to understand this reality, this population cloud of data a lot better. So that doesn't change. That doesn't change. That doesn't mean you use non-parametric methods, then you can slacken off. If you use parametric methods, then with small sample size, not only that you don't understand the reality well, right, because you haven't felt more completely how the population in reality looks like, the parametric test itself is beginning to, rattle like an old engine, right? So it's like about to choke already when you feed it with a small sample size data. So therefore, the outcome is not going to be something that is as reliable as another engine like Wilcoxon or other non-parametric methods that doesn't rattle, even if you fed it with small sample size. That's what we are trying to see here, right? So that's the small sample size robustness characteristics. Okay, what if we have larger sample size? Remember, we desperately needed the central limit theorem, right? In non-parametric case, to help us tide through the situation when the parent distribution is not normal, right? But we can do a lot of hard work by increasing sample size. Then we will be able to obtain a smoother, normally looking sampling distribution of sample. So over here, what happens? Well, we will start with 0 as well, and then we will end with 25, 26, 27, somewhere here. So then we have 20, 15, 10, 5, something. Okay, so roughly speaking, it is like this. Lots of bars, but there is some sort of a pattern. So I roughly can put it this way. Okay, so they all reside on integer grounds. Okay, that's what I must say first. And they show some kind of a profile like this. Okay, so the fact that they rest on integer axis or points on the x-axis doesn't change, right? Doesn't change. So just in case I didn't draw it very clearly or illustrate it very clearly, all the vertical bars, they lie on integer points on the w-axis. So that fact hasn't changed when we increase sample size. Okay, but as we can notice that the range stretches. At first it's finite, 0, 1, 2, 3, because n is 3. But then when n is 10, we get to see 0, 1, 2, 3 until something like 27. Okay, something like 27. So out of curiosity, I increase it some more. Just one more. To see what happens when n is larger, right? Our sense of large is also aided by central limit theorem, so say around 30. So when our sample size gets to 30, then what happens is our range gets even more enlarged. So it's a bit combinatorial. That means, it's a bit like factorial or uh, the combination permutation kind of calculation. Quite explosive, that is, in terms of the range. But of course, the area is always standardized to one unit. So no matter how broad, like normal distribution minus infinity to infinity, you also have only one unit on top. So no surprise here. It is just a distribution. And here I want to again, first of all, partition it 200, 175, 150, 125, 100. Okay, something like this. 125, 100, 75, 50, 20, 25. Okay, so at 225, right, we get these. Then we get here, we get here, something like this. And then there's a drop for a little bit, and then stops. Okay, and in these intervals, sometimes they protrude out. Sometimes they protrude out a little bit, sometimes not. There seems to be some regular protrusions. Okay, like that. Again, all the sticks, all the vertical bars, they rest on integer points. Okay. And then the rest, I can start shading now because it's starting to get very dense. They are somewhat below, like this. Okay. So how do I do this? Well, via Monte Carlo method simulation, right? So just like keep randomly throwing darts at the board, throw 5,000 darts, 5,000 points to run the Wilcoxon test, right, and see what test statistic it generates. Of course, it will be also random, but then eventually it will highlight this silhouette, right, this shape, and that is the distribution shape we want to see. And so that means when n is 10, not that large, right, the shape has already taken place. So that when you grow n to 30, your sample size, right, grows to 30 and all that, the shape somewhat changes little bit, but the general pattern is the same. Right? It somehow peaks at a bit lesser than the maximum range, right? And then it drops a little bit. And the maximum range increases, right? 327 and we don't know what here, but larger than 225. And that is importantly a finite number, not infinity. So that is very different from normal distribution, right? And throughout our discussion, we never talk about normal distribution. No assumption, no insistence that n has to be large, or else no discussion about standard deviation fluctuations or approximation of standard deviations and all that. No, nothing, right? So no assumption. Just give me the numbers and I'll test for you. That's all, right? And of course, my engine, the Wilcoxon calculation engine, is strong. You give me small sample size, I will munch it up without any leftover, right? You give me more data, I can do equally well, but hey, you better have a good, powerful computer to calculate, right, the p-value. But provided that is done, which is going to be more and more available because Moore's law, right, will get more and more affordable computing with higher and higher power as time passes. And that just means that calculating p-value test statistic is getting easier and easier. So that part is no longer a problem. In fact, it's no longer a problem now. And here is we do a little bit more elaborate experiment just to have a look, right? Just have a just to see what is going on when we are trying to perform tests using Wilcoxon. So if we drop a Google pin, it will be like this. It will be like this. If we drop it in, so the test statistic will be here, and the what do you call that? Critical region. So the alpha will be here. and the rejection region will be here. Right? So this is our alpha. Yes. And p-value will be, of course, similar to our interpretation, starting from the test statistic and going towards the rejection region, the infinity belonging to the rejection, like this. Okay, all right. So that's hopefully now you have a better feel of what's going on when you're performing Wilcoxon signed rank test. Okay, that's all for this video. Thank you for your attention. See you in the next video.